Hello Year 12s and welcome back to Mathematics. We're going to be doing some curve sketching stuff this lesson. So this is on page 21 in your blue booklet. So on your blue booklets, this is page 21, which should look something like this. Now over the last couple of lessons we've been talking about our first derivative and our second derivatives and what that means and the applications of that into graphing. So in particular what we said was, and this is just a quick summary, when we get the first derivative of a function, there were three conditions that we could have for our first derivative. It could either be positive, it could be equal to 0, or it could be negative. And so these three conditions, depending on where you are on the graph, resulted in different things. So if it's greater than 0, it meant our graph was increasing. So it was going up from bottom left to top right. It's going like that shape. If it's equal to 0, it was stationary. And then we also talked about a few different types of stationary points as well, and we'll get to that in a moment. And if it's less than 0, it is decreasing, so going the other way. So going from top left to bottom right. We also talked about how if its graph is stationary, there's kind of three main types of stationary points. And so you can either have a local maximum. So if you're at the peak of a graph, so this is our local maximum, local max. We had our local minimum. Oh, wait, the other way. We had local minimum, which is at the bottom. And we had the third one, which was a horizontal point of inflection, which looked like either like this, a little bit dodgy, or like that. So this is our horizontal point of inflection. So we talked about these three different types of turning points as well. And there was a few ways that we could check that. We could either use a table of values, or we could sub it into our second derivative. Now the second derivative, there was also two main conditions. There was actually a third one that I didn't really talk about, but the two conditions were, once again, just like our first derivative, it's either greater than 0 or less than 0. And if it's greater than 0, this tells me that my graph is concave up. So here, this is concave up. So like this. And if it's less than 0, it is concave down. Like this. Now the third condition here is similar to our stationary point, which is if it's equal to 0. Now, if it's equal to 0, we said that it could be a point of inflection. But we needed to check whether or not that was the case by checking the concavity either side of that point. And we'll go through an example of that today. Now, in all of these, when we were going through this, we actually went through a few questions where we were able to sketch a curve based off of finding our first derivative, our second derivative, and doing things such as like determining the nature of our stationary points, and also finding points of inflection on our graph. What we're going to do in this lesson is actually bring that all together in a kind of more formalized way so that we can actually sketch a curve. Now these steps that we have here, if you have a look at 2.1, curve sketching with calculus, these steps are the steps that you would use if you were to sketch a curve and you wanted to find some particular point, to draw it accurately on your Cartesian plane. Now usually in a question, just like the ones that we've done before, the question will actually guide you through these steps that we're about to look at in an orderly fashion. So they'll usually tell you to do a few steps in the lead up to. So these steps, it's probably good to commit to your memory, but often in those questions, they're going to help you through and walk you through those steps before they just ask you to sketch a curve. So let's just go through these steps. So let's start off with these steps. The first step, find the x and y intercepts. Now, finding x and y intercepts, if you remember, the way I find my x-intercept, so here, let's go right actually, my x-intercept. So if I want to find an x-intercept, I'm actually solving for something. I'm solving for f of x is equal to 0. So my x-intercept, I'm solving for my function is equal to 0. And my y-intercepts, that's when I sub in x is equal to 0. So we sub x is equal to 0 into our function, into f of x. Let me write that a little bit cleaner. We sub our x is equal to 0 into f of x. So we want to find f of 0. Okay, so that's our first step. Usually you want to find this. Some of our earlier questions we did, the numbers were a little bit more difficult to actually find this, but often you do want to do this step of finding the x-intercept, finding the y-intercept. Okay, so that's our first step. Second step, we want to differentiate. So just like we did in all these examples, we differentiate to find our first derivative. And that will tell us what the gradient of our function is going to look like at different points. Okay, so second step, we differentiate. And then the third step is that we find the stationary points. So as you guys remember, what we talked up here was, in order for us to have a stationary point, the first derivative, f dash x, needs to be equal to 0. So here I'm going to have, I'm solving for this equation, f dash x is equal to 0. Okay, from there we do that third step, which is determining the nature of stationary points. Now sometimes they'll rephrase it in a different way, but if they ask you to determine the nature or classify the stationary points, this is exactly the same thing. So here, there was two methods that we did. The first method that we did was to test values. So here, what we did was we drew up our table of values. We had x, we had our derivative, and we had our original function, and we put in our values of our stationary points that we got from part 3, the step 3. We put them in, so we had like a and then b, and we tested points either side. And we know that this is 0 and 0. And if it was first derivative is positive, it means that it's increasing. And if it's negative, we know that it's decreasing, and so on. And so using this, we can actually understand the shape of our graphs by looking at the arrows, and it tells us what type of turning points we have. So do we have a local maximum, for example, over here? Do we have a local minimum? Or do we have, like here, a horizontal point of inflection? The second way that you can do this is to differentiate again and get the second derivative and sub in your x values into your second derivative. So here, what we can do is, in the second method that we did, and I think we did an example of this last lesson, is we can sub in our values that we got from our stationary points in the third part, and we figure out what f dash of a is equal to, or an f dash of b. So our stationary points, we sub in those values into our second derivative, because it will tell us if it is a local maximum and local minimum, because of the shape that we're looking at. So if it's concave down, it should be a maximum. If it's concave up, it's a minimum. Now, one thing to add on to here is if your second derivative, if you sub in to your second derivative and you get 0, you might be tempted to think, oh, that must be a point of inflection, but you need to check whether or not it is. You need to check either side of this point to see if it is indeed a point of inflection. Okay, that's the fourth step. Fifth step, we want to determine any points of inflection if requested. So this is only if requested. If the question doesn't ask you to find any points of inflection, don't need to worry about this too much. The way that you do this, what you want to do is you want to find the second derivative, and we're solving for 0. And then just like we did with creating a table of values for our first derivative and our original function f of x, what you want to do is create a table of values for your second derivative, just like this, and check your zeros of the second derivative here. And you just want to make sure that on either side we've got a concavity change. If there's no concavity change, so if it went from positive to positive like it is here, then that means it is not a point of inflection. So we want to make sure that it goes from positive to negative, or the other way around, it goes from negative to positive on either side. And then using all of that, you want to sketch the curve, which is step 6. So that's how we put all of this stuff that we've been looking at over the last couple of lessons into like a kind of formal way of solving these questions. So let's have a go at actually answering a question using these steps. So if you turn over the page to page 22. This is example 20, and this is taken from a 2008 Catholic Schools paper where we've got the function f of x is equal to 15 plus 12x plus 3x squared minus 2x cubed. Okay. So let's go through these parts here. Now, this set of steps, sometimes you don't follow it exactly, but if you're missing certain parts here and there, you might want to fill in certain parts so that you can actually certain parts so that you can actually draw the graph correctly. So for example, if the question doesn't ask you to find the x and y intercepts, you might want to do that at the end just so you can put it into your graph. So let's have a go at this one. So part I. Find the coordinates of the stationary points of f of x and determine their nature. So, as we've done in the last couple of lessons, how do we determine stationary points? Well, we've got to differentiate our function. So let's differentiate our function. So part I. f dash x is equal to. Now when I differentiate my function, I'm just going to go through each term and do my derivative thing. So 15 disappears, it's a constant. When we differentiate, it becomes 0. 12x becomes 12 plus 3x squared becomes 6x minus 6x squared. Okay, now I want to solve for this is equal to 0. The way that we want to do this is we should factorize it so we can see that 0 is easier. I notice from each of my terms I can take out 6, and I'm also going to take out a negative 6. So I can actually just rearrange this and write it in the opposite power order. So here I want to write it as x squared, this term over here. I'm putting this first, and then it's going to be minus x minus 2. Okay. Now that I've done that, I can factorize this even further. So I'm looking for two numbers that add together to give me minus 1 and times together to give me minus 2. So I'm going to put this all together. So I've got, I think the two numbers will be x minus 2 and x plus 2. So here, 6, x minus 2, x plus 1. Sorry, x plus 1 I mean. Okay, cool. From here, what are my stationary points? Well, I can just solve this by looking at each of the factors. So therefore, my stat points are where x is equal to 2, x is equal to minus 1. Okay, cool. Now that I've got that, I want to actually figure out the coordinates. So how do I find the coordinates? Coordinates require an x value and a y value. So I need to sub these stationary points, these x values, back into the original function. So here I'm going to do that. So f of 2 and f of minus 1. Now when I sub in 2 into the original function, I think I get 35. Is that correct? Let me just check that. Yep, I think I get 35. So f of 2 is 35. I sub that in. And when I sub in x is equal to minus 1, I believe I get 5, 28. I think I get 8. That looks correct. Okay, cool. So this tells me that I have a stationary point at 235, and I have another stationary point at negative 1, 8. Okay, cool. Once I've done that, I need to determine their nature. Now this one, I'm going to use the second derivative to help me figure that out. So let's find the second derivative. F double dash x is equal to, okay, let's differentiate my first derivative again. That 12 disappears, and so then I move on to the next term. So I've got 6x becomes 6 minus 12x squared. Okay, the way I check my determine the nature of these points, these stationary points, is to sub in these x values into the second derivative. So let's do that. So I'm going to get f double dash of 2 and f second derivative of negative 1. Okay, when I sub in 2, I believe I get negative 18. Now negative 18, we're just checking if it's positive, negative, or 0. This number is negative, which means that the graph at that point is concave down. Now also know it's a stationary point, so it has to be the point at the top. So this is a local maximum. So I'm going to say, therefore, 235 is a local maximum. Okay, I'm going to sub in negative 1 now. So I'm going to have 6 minus 12 times negative 1 squared, which I believe, oh, hang on. Oh, this should be negative 12. Whoops, my bad. Negative 12x. Okay, cool. I'm going to sub in negative 1, so I get 6 minus 12 times negative 1, which should give me 6 plus 12, which is 18. 18 is positive, so greater than 0, so that means my graph is concave up at this point because this is the second derivative I'm talking about, which means my stationary point has to be the point at the bottom, which is our local minimum. So here I've got therefore, negative 1, 8 is a local minimum. Okay. So that's part 1. I've figured out my coordinates of my stationary points and also determined their nature by using the second derivative. Okay, so we've done part 1. Excellent. So I've found my stationary points by differentiating and solving for it to equal to 0, and then sub those values back into my original function so I get the coordinates, and then I determine the nature by using the second derivative. Okay, part 2. Find the coordinates of the point of inflection. Now, points of inflection, the way that you can find that is by solving the second derivative is equal to 0 and then checking either side of that point. So let's do that. So here, part 2, I'm going to solve f double dash x is equal to 0 when I'm trying to find the point of inflection. So here I'm solving 6 minus 12x is equal to 0. So I move the 6 over to the other side. I get negative 12x is equal to negative 6. divide by negative 12, so x is equal to 1 over 2. Now that I've got that point, in order for it to be a point of inflection, I just need to check that on either side of my point here. So either side of half, I have a change in concavity. So let's write up a table. So here I'm going to have x and my second derivative. So I have a half in the middle, and I know it's equal to 0, and I want to check the values either side. So I'm going to sub in a number on the left-hand side of negative 1, left-hand side of half, and on the right-hand side of a half. So let's pick a number to the left-hand side of a half. So the easiest number to do is 0. So let's sub in 0 into my second derivative. If I sub in 0 into the second derivative, I get 6 minus 0, which is 6, which is positive. Okay, so on the left-hand side, we have concave up. So that means I have on this side, I have concave up, and the way I did that was I checked f double dash 0, which was 6. What's the value I can sub in on the right hand side? Well, the easiest value would be 1. So if I sub in 1, it's the second derivative, I sub in 1, I get 6 minus 12, which is minus 6. And so that is negative. So on the other side, I have concave down. So here we do have a concavity change. So therefore, I know that x is equal to half is my point of inflection. I just want to also find the coordinates of that point. So I need to sub in into my original equation to get that y value, f of a half, which I believe should give you 43 over 2. I think I did this this is why you do things in advance. 43 over 2. And so therefore, my point of inflection is at half 43 over 2. There we go. Okay. So that's part 2. I found my point of inflection. Part 3, sketch the graph, indicating clearly stationary points and the point of inflection. Okay, so let's sketch the graph underneath here. So I'm going to put in, so part 3, I'm running out of space as well, so this isn't good. I'm going to draw up my Cartesian plane, y, x. I'm going to put in my points. So the first point that I had was, I have a stationary point at 235, so I'm going to put a dot at roughly 235. Now this doesn't have to be perfectly to scale. As long as you show all the key features, you should be fine. So 35 and 2. And on the other side, I have a stationary point at negative 1, 8, which should be somewhere around here. 8. Let me write this down underneath here. Okay. I have a point of inflection at a half 43 over 2, which is roughly 21. So I'm going to have a point of inflection at around here. This is a half, and this is 43 on 2. Okay. And starting from here, I can actually start to draw my graph. So here, I've got, if I start from left, negative 1, 8 is a local minimum. So if I can just undo that. It's a local minimum. So I'm going to start from here, and I'm going to go down to a local minimum. And then I'm going to have to cross the y-axis. Now I'm going to find the y-intercept in a moment. And here I've got a point of inflection, so then it changes from concave up to suddenly concave down. And I've got a local maximum at 235, and then from there, I've just got this guy here. Okay, so the additional thing that I might want to add is my y-intercept at this point over here. So y-intercept, we're just going to sub in x is equal to 0 into my function. So here, this number here should be 15. Okay. On top of that, you might want to find the x-intercept. Now, solving cubics like this, so cubics that look like this question here are really difficult to solve. So often if you see a cubic or higher, don't worry too much if it's not easily factorizable. So if there's no easy way that you can factorize it, don't worry about it too much. Mathematicians have barely figured out a way to actually solve cubics easily. Actually they have, but the formula they use is quite difficult. So don't worry too much about cubics and anything higher. Okay, cool. So I've clearly stated the stationary points. I've added on the y-intercept because that one's an easy one to do. You sub in x equals 0, and we've got the graph here. So that's an easy one. Excellent, cool. So that's this first example. We've put together all of our curve sketching techniques. So we've used our first derivative and finding stationary points where it's increasing, decreasing. We've used our second derivative, so point of concavity, and put this all together to form this graph here. Okay, so that's our first example. Turn the page with me. We're now going to have a look at example 21. So example 21 is from a 2010 North Sydney Boys Extension 1 preliminary exam. So Here we're sketching the curve for y is equal to x to the power 5 minus x to the power 4. Okay, so let's go through the steps, these parts here. Part 1, we want to find the x-intercepts of the curve. Okay, how do we find the x-intercepts? Well, if you remember, x-intercepts is when my function is equal to 0, or in this case, because we don't have function notation, we're solving for y is equal to 0. Okay, so let's do that. So here, my function is x to the power 5 minus x to the power 4 is equal to 0. I can start by factorizing out a common term. So if you have a look at both of these terms, I can take out an x to the power 4. So I'm going to factorize out x to the power 4, and I have x minus 1 remaining. So using this, I just need to solve my factors. So therefore, x is equal to, well, what are my factors here? Well, I've got this x to the power 4 out the front, which means the solution to that is 0. And x is also equal to, well, if you have a look at the next factor, x minus 1, the solution to that is 1. And so those are my two x-intercepts. 1 mark, nice and easy. So when I'm finding x-intercepts, I'm solving for when y is equal to 0. Okay, cool. So I've got my first part done. The x-intercepts, I'm done. Okay, part 2. Find and classify all stationary points of this curve. So we're going to, when you're finding stationary points, if you ever see the word stationary points, what do we need to do? We need to differentiate and then solve for it, the first derivative being equal to 0. So let's differentiate. So I'm going to have y dash is equal to 5x to the power 4 minus 4x to the power 3. Now that I've done that, I'm going to factorize it so that I can make it easier for me to solve it. So if you notice both of these terms, I can take out an x cubed, and I've got 5x minus 4. And so from here, therefore, my two solutions are x is equal to 0 and x is equal to 4 over 5 by solving those two factors. Okay, cool. So we've got that. Now that I've done that, I need to also, so we've found our stationary points, but we also need to classify them. We need to classify them. Now this time, I'm going to use the table method that we talked about in the first couple of lessons. So I'm going to draw up my table. I'm going to have x, the first derivative of x, and in this case, it's y dash, and my original function, so here y. So I'm going to put in my two stationary points. The first one is 0, and the second one is 4 over 5. I know at these 2 points, the first derivative is equal to 0. For the y value, I just need to sub these back into my original function. So here, I'm going to sub in f of 0, which gives me 0, and f of 4 over 5, which I've done in advance, which is negative 256 over 345, I believe. 3125. Whoops, my bad. So here, this is negative 256 over 3125. Let me write it a little bit bigger so we can see it a little bit better. Maybe I'll expand out this. Negative 256 over 3125, and over here it's equal to 0. Now that I've done that, I'm going to use this table. Now what do I need to do with this table? I'm going to sub in values that's either side of my stationary points to figure out with a sign of the first derivative. So let's sub in a value that's less than 0. So here, I'm going to sub in x is equal to negative 1. When I sub in x is equal to negative 1 into my first derivative, what do I get? Well, I get negative 1 times 5 minus 4, which is negative 9. So negative times negative gives me a positive. So on this side, the graph is increasing. So first derivative tells us if the graph is increasing or decreasing. Increasing, decreasing. Okay. Let's pick a number between 0 and 4 over 5. A nice and easy number might be 1 over 5. So let's pick in 1 over 5. Let's sub it in. 1 over 5 to the power 3 gives me 1 over 5, which is positive. And 1 over 5 times, 1 over 5 times 5 minus 4 gives me, what does it give me? It gives me negative 3. So here I've got positive times a negative. So positive times negative will give me a negative. So this side, it is a negative. So here I've got, it goes down. Okay, on the other side of 4 over 5, let's pick a number. An easy one would be 1. So I sub in 1 into my original function. I get 1 times 1 times 5 minus 4, which is a positive once again. And so this side is going up again. Okay, we want to classify these stationary points. So my first one over here, 0, 0. What is it? We go up and then we go down. That's a local maximum. And on the other one, I've got 4 over 5 and negative 256 over 3125. It goes down and then back up. This is a local, because it goes down and then back up, it is a local minimum. So here, 4 over 5, negative 256 over 3125 is a local minimum. Okay, cool. So I've done the second part. I've determined the nature of these stationary points. Okay, third part. Find the x-coordinates of all points of inflection. If you see the phrase points of inflection, we just need to find the second derivative and solve it for equal to 0. So here, second derivative, I'm going to differentiate again. I'm going to get 20x cubed minus 12x squared. And I can factorize it. I'm going to take out 4x squared, and I'm left with 5x minus 3. So therefore, my two solutions are x is equal to 0 and x is equal to 3 over 5. So I want to find the x-coordinates of my points of inflection. I found the x-coordinates, but have I shown that they are indeed points of inflection? No, not quite. In order to do that, we actually need to check that on either side we have a concavity change. So I'm going to draw up my table again, but this time for my second derivative. And with the second derivative one, all we need is x and the second derivative. I'm going to put in my two zeros here. So I've got 0 and 3 over 5. I've got 0 and 0. Okay. Let's sub in a number which is less than 0 on the left-hand side. So here, the number less than 0 would be minus 1. So I've got 4 times negative 1 squared, which is 1. So that's positive, times 5 times negative 1 minus 3. So that gives me a negative. So this side, it is negative. It is concave down at that point. Okay, let's have a look again. Let's have a look at the next one. So it's between 0 and 3 over 5. What's the number between there? 1 over 5. If I sub that in, I get 4 times 1 over 5 squared, which is positive still, times 5 times 1 over 5 minus 3, which is a negative. So here it's concave down again. So that point at 0, is that a point of inflection? Well, if you have a look on the left-hand side, we've got concave down. And on the right-hand side, we've also got concave down. So therefore, x is equal to 0 is not a point of inflection. That's the conclusion I can make. In order for it to be a point of inflection, the second derivative on either side needs to be different to each other. They can't be the same thing. So let's check on the other side of 3 over 5. So a number bigger than 3 over 5 would be 1. So if I sub in 1 into my second derivative, I get 4 times 1 squared, which is 4, which is positive, times 5 times 1 minus 3, which is 2, which is also positive. So on this side, it's positive. So do I have a point of inflection here? Yeah, I do. So x is equal to 3 over 5 is a point of inflection. Because if you notice here, this time, I have a negative on one side and I have a positive on the other. We have a sign change. So because we have a sign change in the second derivative, x is equal to 3 over 5 is a point of inflection. Now, if you have a look back at the question, they just asked me to find the x-coordinates of all points of inflection. I don't need to find the actual coordinates. So I don't need to sub this number back into my original function. I've actually done with the question here. So I figured out that x is equal to 3 over 5 is a point of inflection. Okay, so that's part 4. Part 3. Part 4. Hence, sketch the graph showing all important features. So let's put this all together. I'm going to draw up my Cartesian plane. Now, let's start from the top. From the first part, I've got my two x-intercepts at 0 and 1. So I'm going to draw x-intercept at 0, x-intercept at 1. Now, the reason why I'm drawing this quite far out for 1 is because if you notice my following two parts, my stationary point is at 4 over 5, which is between 0 and 1, and my point of inflection is at 3 over 5, which is between 0 and 1. So I want to stretch it out so I can just see those points a little bit clearer. Okay, so let's have a look at the second part. Second part, I have a local, I have my stationary points at 0 and 4 over 5, x is equal to 4 over 5. So I'm going to put in x is equal to 4 over 5 here. And this local minimum at that point is negative 256 over 3125. So I've got a point down here. Okay, cool. Okay, once I've done that, I'm going to put in the thing from the third part, which is my point of inflection, which is at 3 over 5. Now, at this point, you probably do want to put in the values back into the original equation. I lied. When you put that in your calculator, I believe you get negative 162 over 3125. So here, I've got my point of inflection is down there. And so now that we've done that, we can actually start to fill in our graph. So we start from here. On the left-hand side of 0, it's concave. It's increasing up to 0. So I'm looking at my this table over here, this table here. On the left-hand side of 0, it's increasing up to 0. And then we've got a local maximum at that point, and it goes down. When it reaches 3/5, that is my point of inflection, so it's going to start turning from concave down to suddenly concave up. I've got my local minimum at 4/5, and then it goes back up to 1, which is my x-intercept. So there we go. That is our function. Y is equal to x to the power 5 minus x to the power 4. So there we go. That is my graph for this particular question. So when you're dealing with these questions, read what the question asks you to do. If they don't give you any instructions, it's helpful to go through those steps that we identified. So finding x and y intercepts if possible. The y-intercept should be a lot easier than the x. Then differentiating and solving for when the first derivative is equal to 0. So that's our stationary point. Determining the nature, so putting it either into this table like we did in this example, or putting it in the second derivative. And then working out whether or not there's a point of inflection based on whether or not the question asks. So that's how you can use this particular method to actually help solve or help sketch a curve. So there's a few questions here in your textbook. Please have a go at those questions for me, and I will hopefully see you next lesson. Bye.